So you now understand why the word strain hardening is there. It is a part of the plastic region from the end of the yield point to the ultimate strength point. So if you load the material at any point in this region, then you have loaded it to a stress which is higher than the yield point and lower than the ultimate point. And when you offload it, then you go to a parallel line and there is some permanent strain. Now when you use this material again, then you will find that its yield strength has increased. So you have strengthened the material, or you have increased the strength of the material. Increasing the strength means you have increased the hardness of the material also. So by applying permanent plastic strain, you increase the strength or hardness of the material. Therefore, this is called strain hardening, increasing the hardness by applying permanent plastic strain. So now it is very clear: the elastic region, the yield region, the strain hardening region, the necking region. So this is your total complete curve. And of course, the true stress, true strain curve is also here, and the engineering stress, engineering strain curve is also here. So now you really know a lot about these things. So let us do an example, right? That is always what you like. I sometimes ask a question which is sort of a joke to me. If I ask you, if I were in the class and I ask you, how many of you really like or love mathematics, linear algebra, differential equations, differential calculus, integral calculus, how many of you really love it? If you are very true, maybe 1 or 2 hands in the whole class of 40 stand up, or maybe none of you. So all of you say that we don't like math. All of you then say, majority, that we don't like math. Okay? So then let us make a policy from now on that all questions in the course will be descriptive questions. I will not ask any numerical problems. You do not like math. So I will ask every question about understanding of the material. So you write long answers. You think and you write long answers. So do you like it? So if I am in the class, then I am smiling, you are smiling, right? So this is very strange. You don't like math and you don't like descriptive questions. So I should not give any numerical problems. I should not give any descriptive problems. I should just come here, teach and go and give everybody an A, right? So you don't know what you like. If all of you like to have numerical problems in every course, then you like math, right? You are just afraid of it for no reason. Okay, now to the example. Compare the engineering stress and strain with the true stress and strain, right? Sorry, this is a typo mistake in the book. True stress and strain. For the tensile test of a low carbon steel that has the following test values. You have a low carbon steel, you have performed a tensile test. Load applied is 17,000 pound force. Initial diameter is 0.5 inch. Diameter at this load is 0.472 inch. Okay? So you have not gone to fracture, you have gone to this load. The original diameter is this and the diameter at this load. So this is the final diameter. So these things are given. The initial diameter of the specimen, the final diameter of the specimen, and the final load on the specimen. Load. These things are given and you have to find the engineering stress strain and the true stress strain. Okay? So this is it. So again, please read the question, take down the data, write them. This is equal to this, this is equal to this, write it. And what is the unknowns are there? Go back to the equation. Don't go forward on any page. Go back to any previous page where you have equations and then solve it. So that is always the case, right? Solve it. And then let us see how it will happen. Okay, so now you have removed the pause. Most probably, you paused my video lecture. You went to your page and pencil and you solved it. Okay? What is engineering stress? What is engineering stress? F upon A naught. F upon A naught. Do you know F? Yes, you know the F. Do you know A naught? You know the D naught. So pi by 4 D square or pi r square. So you find A naught from here, F is given, so F divided by A naught is your engineering strain. Done. What is the engineering stress? Sorry. Engineering strain, what is the formula? Delta L upon L naught. Change in length upon original length. Do you know the original length? No. Do you know the change in length? No. So for now you cannot solve it. So leave it for now. What is the true strain? True stress. What is the true stress? Force upon the current area. Force upon the current area. Force is known? Yes. Current diameter is known? Yes. Current diameter is known. So pi by 4 d square or pi r square is the AF, the current, or AI, the current one. So current force divided by the current area, you have the true stress, right? What will be the units? PSI, pound per square inch. And if there are thousands of numbers, you can write KSI, kilo pound per square inch. Kilo pound per square inch, right? Now, what is the value of true strain? What is the value of true strain? True strain. It was ln of Li upon L naught. Remember, ln of Li upon L naught. It was also equal to ln of A naught upon Ai. It was also equal to ln of A naught upon Ai. Remember, I told you we will discuss it again later. But if it is ln of A naught upon Ai, then you have the value of A naught from here, you have the value of Ai from here. So ln A naught upon Ai, and you have the true strain also. Now, before we proceed further, I said we will comment on it that ln Li upon L naught is simple because it was integral dl upon L. So 1 upon L dl is ln of L, and ln of L from L naught to Li is ln of Li upon L naught. So that was okay. Now, why is ln of Li upon L naught the same as ln of A naught upon Ai? Have some of you thought about it? So pause and think about it. You were to think about it at that time when we were discussing true stress strain. But if you did not think about, pause my lecture and think that can you prove that ln of Li upon L naught is the same as ln of A naught upon Ai? What is the reason? If I ask you, totally forget we are in which course. If I ask you, in all of science, physics, chemistry, whatever, biology, geology, in all of science, what are the two most fundamental laws which apply to every single science in the world? Very strange question, right? Two basic fundamental laws which apply to every engineering and science in the world. Does not matter whether you are in petroleum or civil or chemical or mechanical. Every science in the world is based on two fundamental laws. Yes, those of you who have guessed it right, everybody knows it. But some of you are not exercising your brain as much. Conservation of mass, conservation of energy. Law of conservation of mass, law of conservation of energy. That whatever experiment you do, thing can change shape from one part to the other. You took a plate, you did some drilling, you now have a plate with a hole. But you have some extra material which has come out after drilling. So if you take the total mass, it will remain the same. Similarly, whatever is the energy amount, some heat can change into light, some light can change into heat, some heat can change into electricity, whatever, but the total amount of energy can never change. So law of conservation of mass and law of conservation of energy. So we go to the law of conservation of mass here as an explanation. If you have mass, so you see, you are doing the tensile test. You are increasing its length, you are decreasing its dia. Is the mass changed? No. Mass remains the same. Now, if you, right, which also means what? Volume remains same. Volume cannot change, right? So this is the physical reality. Because mass cannot change, so the volume cannot change. The dia is changing, the length is changing, but the volume of the piece cannot change. So this is the basis. Volume remains constant throughout the tensile test. You can keep on changing the dia, you can keep on changing the length. So you can write A naught into what? Volume is what? If I take the area of cross section multiplied by what to get the volume? Right, length. You see, it is a cylindrical piece. So volume is area, cross sectional area, the circular area into length. So A naught L naught is the initial volume, volume at the start of the experiment. The area is A naught, the length is L naught. So A naught L naught is the initial volume. At any time later on, it is the current area AI and the current length Li. So A naught L naught is equal to AI Li. Do you understand? Because volume is constant. So therefore, A naught into L naught is equal to A naught into L naught is equal to AI into Li. Therefore, Li upon L naught is how much? A naught upon AI, right? So you have proved it. So now you can use that result. Now the next part. How to find the engineering strain, because you don't have delta L upon L. You don't have delta L upon L, right? You have only areas. A naught is known, AF is known, but not the other values. So how do you do it? So okay, let us do it. Here, let us do it. Delta L upon L naught. Delta L upon L naught. Delta L is what? Li minus L naught, right? You can write it. Li, current length minus initial length. So Li minus L naught upon L naught. Yes? So now divide it and break it into two parts. This is Li minus L naught upon L naught. So Li upon L naught minus L naught upon L naught. So it is Li upon L naught minus 1. The engineering strain now is Li upon L naught minus 1. And Li upon L naught, can you write it in areas? Yes. Li upon L naught is A naught upon Ai. So you see, this is the beauty of simple math. First, a basic conservation law of conservation of mass, which also means law of conservation of volume. Once you apply that, and then simple arithmetic, initial volume is equal to final volume. So now you can solve all. So yes, if you now look at the solution, then simple things, you find the A naught, whatever is the value, you find the AI, whatever is the value. Then engineering stress is force upon initial area, you find the value in PSI, you can write 86.7 KSI. Engineering strain is delta L upon L naught, but then it is Li minus L naught upon L naught, so it is Li upon L naught minus 1. So it is A naught upon AI minus 1, and A naught AI you have done, and here is where we are explaining it. So now you have engineering strain. And true stress is of course force upon current area. True strain is ln of Li upon L naught, which was ln of A naught upon AI, right? So this is a brilliant example, that in the example we are not giving you any lengths, not the initial length, not the final length. We are only giving you the initial diameter and the final diameter and whatever is the force applied, but from there you can find the true stress and true strain and so on. So please try to do these on your own, not with my help. Please, before next lecture, try to go through the current lecture and so on always. Of course, the next lecture we have the quiz also, so prepare for that. And for today we are stopping here. We'll see you next time inshallah. Ma'as salama.